Thank you very much, Mary Lane. It's a pleasure to be with you all this evening. And I'd like to take some minutes of your time and sort of go over just a brief overview of our biomedical engineering major so you guys can get a sense of what this major is like. This is a product of approximately 10 years of research by almost every faculty member in our department. And we think it represents a transformative vision for creating the biomedical engineers that are essential for the types of industry, medical, and academic research careers that are going to be so essential in this new 21st century. And so many of you may have heard of biomedical engineering before, which is why you're considering this as a major. But I'd like to highlight a couple things that make it different from traditional life science and engineering disciplines. With respect to biology, biomedical engineering is inherently more quantitative and analytical than the ways that biology is currently being investigated. But I think more than that, the biomedical engineer, is really focused on controlling the processes that they identify and driving change in those processes. And really, it's about how to use those biological processes that they are understanding to restore or improve function, in particular human health. And so from respect to other engineering disciplines, biomedical engineering is unique in that it focuses on human health applications, but more than that, it's about being able to engineer robust solutions within highly variable and uncertain environments. And so the one great example we have right now is the coronavirus situation, where you have a highly variable and uncertain course of the disease, the infection rates, all of these things that basically demand engineering solutions that can work robustly despite some of the unknowns that are in this system. And so it's really important for biomedical engineers to thrive in that capacity. Furthermore, biomedical engineering exists in an inherently rapid innovation cycle. So the tools that we develop today are going to be very commonplace very soon. And so it's very important that biomedical engineers can stay on top of the innovation cycle. Furthermore, biology, in the way that we study it as an engineering system, is inherently moving as a target. So what you look at on one day could be very different the next day. And as an example, this set of images shows one cell, looking at that little yellow dot, differentiating within a 30-minute period. So when you are tracking these cells, you might miss this cell if you're not looking very intently over even such a short amount of time. So biomedical engineers also practice their engineering, much like one might think of a combination between an architect and an engineer. So when we think about an architect, nobody would want to build a house without an architect. Nobody would want to build a building without an architect. Architects are fundamentally important for synergizing information across so many different discipline streams, and at the same time is able to create within that knowledge space so that they could to develop a synergistic work. And so the way that we articulate biomedical engineering within our curriculum is we teach you how to be able to not just analyze complex engineering systems, but how to represent them in a way that allows you to communicate them across disciplines within your very convergent research teams, but also to be able to communicate them to the next step, manufacturing, doctors, other kinds of stakeholders. Furthermore, we have to articulate the natural engineering principles that are naturally occurring, that meet the function that whatever your system is trying to integrate with. So this is a multi-scale process. It's down to molecules, cells, all the way up to an organ system. These systems are dynamic. They have parts that are uncertain, like I mentioned before. And when you were trying to replicate these systems in various technologies, you have to deal with soft materials, hard materials, and circuitry to control them. We also incorporate experimental design, which is, we think, essential for knowledge creation. So this isn't just about building technology, which of course it is an integral part, but also thinking about how would you design experiments to test actual hypotheses that those technologies would use, and therefore not only demonstrate the utility of the technology, but you create new knowledge. And being able to converse in both of those skill sets is really important for the biomedical engineers of the future. We are also intimately responsible for being able to work within the human health constraints for engineering solutions. So these are things like regulatory restrictions, but they're also concepts and complicated realities about the human body and how its organ systems interact. One of the common themes of engineering at Cornell is breaking the rules. And we don't mean this in the sense that we're trying to do something different with respect to human experiments. But what we really mean is that the type of rules that govern how the human systems, even at any of those scales, interact are fundamentally different from the idealized approximations that you might see in other engineering disciplines. And so it's really important that we can learn how to actually handle this system using the right rules to be able to generate understanding. And finally, it's really important as biomedical engineers that we practice creativity. Just like an architect is trying to build a building that's going to stand the test of time, but also stand the aesthetics of the era, biomedical engineers are really it really must be able to generate ideas from lots of different places to be able to meet these targets. And so how do we do this? So we developed a three-pronged approach that we think is really important for making this integrated biomedical engineer. So it starts with transcurricular pedagogy. Now that's a big word that means that our faculty are actually well trained in not only what to teach, but how to teach. And we're specifically aware of how to make use of all the latest technologies, not just things like online virtual instruction, but really how to engage content in a way that it makes it meaningful, but also an opportunity for students to be able to work together in how they are learning, okay? We also designed our curriculum from the application space first, okay? So when we were looking at our major and trying to figure out what is necessary for this 21st century biomedical engineer, we went to industry and we went and looked at what industry it finds essential for like the next 5, 10, 20 years. And from there backed out what are these important knowledge spaces, technology spaces, and expertise that these students need to have. And so when we found that information, we decided to show students all of these opportunities and challenges first, so that when they start the major, they're already aware of what they want to move in deeply. And this is very different than traditional engineers, which will focus on theory first and applications at the very end. And then the third element is called experiential learning. So the classroom is just one place where you can learn tools and theory to be a good engineer. But we think it's essential that you expose yourself to an experiential learning activity, but not just to perform in that activity, but actually to reflect in that activity and be able to bring the curriculum into that space, but also to gather from that activity back into the curriculum so that you're actually thinking and doing like a biomedical engineer would in terms of being able to add value to whatever engagement that you're in. And so if you looked at our curriculum at a glance, it would look like this. So at the bottom, we have a foundational engineering core curriculum. So when you enroll in the engineering college, you can basically choose any engineering degree you want or major that you want and take the fundamental core curriculum towards that engineering major, and then you apply to affiliate into a major. Once you do that, you would, for example, biomedical engineering, you would start in our major with what is called the cornerstones. So the cornerstone courses represent all of the fundamental knowledge and application spaces of each of the concentrations in our major, so that you will be able to dialogue between members of those different concentrations, which in turn represents people from those different industry spaces. Then you pursue a parallel track of our core engineering sequence that's focused on the analysis of biological systems. and then in parallel, a concentration. So these concentrations, again, come from a specific interdisciplinary set of expertise. And then finally, we bring both of these back together again, and you pursue a design and practice project where now each of your team members have specific expertise, and you're well trained to be able to pursue the design project at the end of the curriculum. And so in terms of that sequence strategy within the core, we're basically teaching you how to understand the human's body as an engineering system that is a multi-scale system. So everything from molecular to organ system scales, to learn about those feedback networks, how to deal with uncertainty and recognize variability in those systems, develop engineering skills for those open-ended problems, okay? But also we teach you about key human health factors that impact every engineering solution, whether you're trying to build a prosthetic implant or design a vaccine. Every single one of those applications has to deal with these sequences, dealing with the immune system, coagulation, infection, wound healing, regeneration. So these are captured within that core. So no matter what system that you're interested in, what concentration you're interested in, you will be able to engineer with those features in mind. So if we look at the concentrations, we have 4 of them, and they each have an acronym, and they deal with those 4 different application spaces within this major. And so I'll sort of move into that with this next slide. So molecular cellular systems engineering, this is where data science meets bioinformatics, meets complex cellular models. And so this is us teaching students how to not only quantify how complex biology is changing, but to be able to engineer strategies to manipulate that those dynamic systems to, say, shift the differentiation of cells towards a pathway of your choice, to think about designing precision medicine applications that will work for subsets of patients, all of these kinds of application spaces. And so we've had students working in this space, not only in academia as well as industry. So the next concentration is biomaterials and drug delivery. So here, we're not just thinking about making materials that are going to be implanted in the body to perform, say, just a structural function, but we're actually intrinsically interested in how these materials engage with the host. So this is a major failure mode of biomedical materials. It's very important to be able to control how that material engages the human body for a particular response, whether you want to release drugs at a certain time, whether you want to take materials and have them remodel over time to affect a host. And so the biomaterials and drug delivery concentration teaches students about novel materials, but also how to characterize those novel materials and how to fabricate with those novel materials. And one of those examples I was just showing was 3D tissue printing. So the third concentration is biomedical imaging and instrumentation. So this concentration is focused on designing and implementing novel instrumentation that can quantitatively engage the human body. Okay, so this is for disease diagnostics, for prognosis, anything that you wanted to be able to ascertain from a patient, and perhaps you would like to be able to do it minimally invasively. This also is looking at constructing algorithms that can maybe work with those complex systems to be able to find key performance criteria, et cetera. And so this is an example of a microscopic technique developed in the Schaefer Nishimura lab, where they can actually laser ablate tiny vessels deep inside a human brain without injuring any of the other tissue structures, as a way of studying hemorrhage formation. And so Chris could tell you a little bit more about research when we go to him. And the last concentration is biomechanics and mechanobiology. And so biomechanics and mechanobiology is focused on not only understanding the complex material properties of the human body, whether that's soft tissues or hard tissues, but we also try to understand the molecular and cellular processes by which those material properties change, whether through disease, whether through aging, whether through embryonic development. And it's very important to be able to monitor those variables, but also to control those, because designing an implant for a child might have very different parameters that you want to replicate than designing for a senior citizen. And these levels of nuance are going to be really important in how we also engineer control of those implants when we move from something that's purely passive to highly active and bioresponsive. So those are the concentrations. Now, we also talked about experiential learning, and here are just some of the examples of experiential learning that our students have done over the course of their undergraduate career. So many students are interested in doing laboratory research or becoming a teaching assistant, and many of these students use these experiences towards an honors thesis. Our students are often very active in the Biomedical Engineering Student Society, as well as educational outreach activities where we engage the local and regional school districts. We have a fully staffed science center here in Ithaca that students can make exhibits for. And we also have a variety of stakeholder groups that reach Cornell all the time through a system called Engaged Cornell. I mean, this is everything from 4-H groups to community groups that are focused on cancer, lots of different opportunities. Cornell is also unique in that we really have a well-developed system of project teams. These are teams that are legacy groups that have existed for many years, and they develop their own sort of alumni following as a way to bring engineering into an experience, but also to use that experience often in a competition. So each of these have teams that are developed from students. They're student-led, and they compete in national competitions for those various challenges that are put out every year. And so getting into that part, it's also very important for biomedical engineers to be able to create ideas, and then from ideas towards designs, and from designs to actually building and testing technology. And so this is something that you do as an integral part of your career as an undergraduate in our biomedical engineering major. And so here are some example images of students that are working in our state-of-the-art design, fabrication, and testing facilities that we have housed in Weill Hall that you will be able to access. And so we actually teach our design embedded throughout the curriculum. In fact, you can take, even as a freshman, you can take a course in our Intro to Biomedical Engineering that has a design showcase as part of its curriculum. But also we teach you directly on how to use biomedical instrumentation, how to perform measurements and design hypotheses for those measurements. Moreover, every single concentration has its own practicum laboratory that you would take as a senior that gives you an actual practical apprenticeship experience that is designed to give you ready-made tools to fit right into those exact positions that you would have at the end of your professional training. And then we bring all that together in a 2-semester design sequence. The unique feature about this design sequence, though, is that you'll actually have teams of members of those different concentrations. So just like in the job world, you will have a team of individuals with unique experience, which means you're going to be simultaneously responsible for unique knowledge sets within your team, but also you're going to be able to develop a synergistic product that's better than what any one of you could have done. And this is essential for students to practice doing as a student before you move and do this in your career. And so the problems that you'll get in these design teams can be posed by industry and hospitals, and again, allow you to use those authentic design and fabrication facilities to actually build and test your device towards those applications. And so every year we have a showcase at the end of our senior year where you can actually present those designs to those stakeholders which came up with those problems in the first place, and see how they take it and how your system works. And so it's a great opportunity as a sort of a showcase for all the work that you've done. And so you can see students talking anywhere from actual hardware devices to biological techniques, and it really runs the gamut depending on those concentrations. And so there are a number of paths that you can also take through our major. So some examples are like pre-health careers. So we have a number of students that would pursue pre-medicine track through our major, because it's designed to be able to facilitate that with taking a very small number of additional classes. We've had students study abroad. We've done co-ops, internships, a number of students do an honors thesis, as I mentioned before. And then there's also a variety of breadth that you can obtain, either doing a combination bachelor masters. There's a number of minors that you can take advantage of, whether computer science or even in life science with genetics. And we've even had students do a combination from bachelor's all the way to MBA. So again, this program, even though it's only a few years old, has been, we've been very proud of our success of our students so far. Pretty much everyone that we've been able to assess has been able to attain their next career step. So we're very proud of what they've been able to do. And with that, we'd like to, well, I guess I'd want to do questions, but I want to get Chris to go to his part next. So Chris, do you want to take it away from me, and then we'll do questions?